Professor John Leonard is a professor in mechanical and ocean engineering in MIT Department of Mechanical Engineering. He got his bachelor degree from University of Pennsylvania and the PhD from Oxford. He became a IEEE fellow in 2014 and AAAS fellow in 2020. Professor John Leonard is also a technical advisor at Toyota Research Institute. So I want to say Professor John Leonard is really a pioneer in SLAM research and also top leader in robotic research. When I start to work on SLAM myself, I start to read papers from John. And he has given so many keynotes and distinguished lectures and others. If you don't know too much details about John Leonard, you probably can see the list of his students. So if you look at the list of his students, you will see many famous people over there. I think John has a lot to talk about, want to talk about today. I will give the opportunity to John, and you can decide exactly what to talk about. And sure. Hopefully everyone can learn something from John's research career and also his work in SLAM and other autonomous driving and so on. So John,
thank you
to share your slide. Yeah.
You're very kind. Can you see my slides?
Yes.
Great. So let's see. So I titled my talk "Towards Self-Improving Object-Based Navigation and Mapping." And so my dream for a long time has been a robot that can understand the world, sort of spatial intelligence, being able to know what is around you, where am I going, how should I get there? Going a long time, I've been sort of obsessed with this problem. And so just a little bit of background, and thanks, Shoudong, for the introduction and the invitation. And Sydney is, as I'll say in a minute, Sydney has a really special place in my heart, UTS and University of Sydney and all the colleagues there. But I've been, since coming to MIT in 1991, I've worked with autonomous underwater vehicles. I was also a team leader for the MIT DARPA Urban Challenge team. And so self-driving is a whole nother topic. And I've done a lot of work on SLAM. And this is a video from 2006 kind of time frame, maybe, no, sorry, yeah, 2011 maybe, of a robot like being navigated around the second floor of this data center using stereo vision to do sort of SLAM with a pose graph and using visual features to get geometric constraints and then some loop closing, stitching that together. This was work with my student, Harder Johansson. And this problem of how a robot navigates around, correcting the uncertainty in its motion and closing loops, building models, and then trying to use those models is to me really like a core challenge in robotics. And so I've been fortunate in my MIT career to be involved in many different things, and I'm part of the CCL lab. But I've also had a chance to work with Toyota Research Institute since 2016, where I'm currently a technical advisor. And I actually just finished a year on sabbatical. I was half-time MIT working in my lab with my students on some papers that I'm going to try to tell you about, and half-time with Toyota helping to mentor a new team in the self-driving and the automated driving space. And I can tell you about that. So for me, so I think this is Dissa in the picture here in the back. So does anyone know where this picture was taken? So in University of Sydney, and this was my advisor, Hugh Durant-White, who was just a dear, cherished friend and had such an influence on my life and on so many of you too. This was at the ISER conference in March 1999, which was in Sydney. It was my first trip to Australia. And it was just an utterly life-changing experience. And it's hard to capture the sort of excitement that burst onto the scene. I think it was a real inflection point that there became huge interest and energy in SLAM right after this. And in fact, if anyone knows the name of Juan Domingo Tardos from University of Zaragoza, Mingo and I met on the elevator leaving the conference on the last day. And well, we were in the same session, really early SLAM results. And Mingo and I decided to organize a workshop at ICRA 2000. And that drew a lot of folks, including Sebastian Thrun, and then a whole sort of community emerged. And so Sydney is a special place in my heart. I haven't been back in 10 years. So the Robotics Science and Systems Conference was 2012. And this is with David Battle, who was an MIT postdoc, who's an Australian with a very successful business for marine autonomous software based in Sydney. And I saw him a few weeks ago at MIT. And so when I think of Australia, I think of SLAM. There's so many great SLAM researchers, going back to Alex Zelinsky and obviously all the ACFR folks, Eduardo, Stephen Williams, and Shoudong and Dissa. And also Mike Milford is a collaborator and friend in Brisbane. And the really, you know, I think, so I promise to come in person when I can. And so for today, before I talk about some recent MIT work, since I was just on sabbatical at MIT with Toyota, I wanted to give a little intro on some Toyota work, which hopefully might be interesting to you folks. So if you've heard of Toyota Research Institute, TRI, I helped mentor, lead the human-centric intelligent driving team, whose director now is Avinash Balachandran, who's I've been working with him closely for 3 years. Ryan Eustace, who's a pretty famous SLAM researcher, was kind of my boss for a while at Toyota. Ryan's led our automated driving team and is now in a new role, helping to steer Toyota Research Institute's human-centered AI activities. And if you don't, TRI was launched in 2016. This is a picture of Gil Pratt, who formerly led the DARPA Robotics Challenge with humanoid robots in the US, and Akio Toyoda, the president of Toyota. And TRI was founded to sort of try to set the research frontier for Toyota to really think long-term, high-risk, high-reward strategic research, and not just in the driving space, but also in robotics, energy materials, and AI. And so TRI has grown a lot. I was one of the first 6 folks on board in 2016. We grew over 300 people, had a big automated driving team that's now part of the Woven Planet family of Toyota companies. And TRI today has a number of divisions, including energy materials, robotics, human-centric AI, human interactive driving, which I'm going to talk about, machine learning, and some supporting activities. And I have a little sample video from the robotics team. So this is the work of my colleague, Ross Tedrake, who's on sort of a partially from MIT to work with Toyota, and Max Bajachara is the vice president of robotics. And so I'm just this is not my work, but this is a little flavor of some of the robotics work that TRI is doing. It's all public. So that last bit with the robot giving the person a hug, part of our philosophy is to have technology that complements and amplifies humans, not to replace humans. And so we try to have that theme also in our driving research. So, so briefly, the human-centric intelligent driving team, our investment sort of thesis, our premise is that fully automated level 4 self-driving is going to take a very long time. And I've written about this and talked about this. And even though self-driving is here today, if you know where to look, San Francisco, Arizona, Cruise, Waymo, some companies have very highly capable kind of minimum viable prototype deployments, but they're still relatively small scale. And because of all the corner cases and challenges, you know, I believe that it's going to take a long time for fully automated driving to roll out, you know, across, say, the US or even worldwide. I think there's an opportunity to take the advances in AI and robotics and machine learning and perception, prediction, planning, and try to change the driving experience, both for safety and for improving the enjoyment, the love of driving. And ideally, what I'd love to do is make people better drivers. Imagine a car that could teach a person to be a better driver. And so we have this concept where we try to blend the best of human control and automated driving techniques to try to keep the driver really engaged, but amplify their capabilities. And so as one example of this, we have a project in automated drifting. So this is a video released earlier this year. The team Avinash led and I helped with is heavily indebted to Chris Gerdes, who's a professor at Stanford, who was the first academic to do automated drifting. And so we're using an automated Supra with some a novel nonlinear model predictive control. And this little video gives a little snippet of what the guys have been up to in California the past year or two.
There is much to learn at the extremes, where expert drivers can handle what most drivers cannot. Our team is developing on-demand autonomy to prevent car crashes, temporarily giving an ordinary driver
Whenever you're ready.
the drifting skills of an expert.
One of our team members, by the way, is an alum of the ACFR. Alex Green is from Sydney. He's from Australia and he went to Sydney. It's a very small team.
Look good. That look good.
Copy that.
Let's go again.
So to give you a little peek behind the curtain of what's going on with this, and then I'll try to say how it kind of relates to the sort of larger vision of amplifying human behavior. Here's a drone shot of the car doing one of the drift maneuvers. Now for this set of experiments, the obstacle positions were mapped a priori. We have related parallel research doing sort of real-time perception and connecting that to planning of static and dynamic threats. But if you can see on sort of the time lapse here, there are these different phases of the drifting motion. And in the next picture, I'm going to show you a trajectory that's color-coded that shows the 3 different phases. So blue is grip driving, conventional driving. Orange is when the handbrake is used to trigger bringing the car into the drifting regime, which I'll show in a second when I do the phase portrait. And then green is the actual nonlinear model predictive control drifting, and the controller can sort of work across the drifting and non-drifting kind of spaces to provide sort of a unified control architecture for high performance driving. And this was a completely new field to me before Toyota, and I'm just barely hanging on by my fingernails to understand some of the details. But folks like Chris Gerdes talk in terms of the phase portrait, where you have the yaw rate and the side slip of the car. And a conventional car, which is driving restricted to the regime with strong grip of the tires, is restricted to the sort of polygonal regions in the middle here, where there's smaller deviations of yaw rate and very little side slip. But what a drift driver, like a professional drift driver, can do, and which we want our algorithm to be able to do, and we're taking steps in that direction, is the entire green trajectory here are places where it's beyond conventional human sort of steering control, but yet the algorithm through its control and its predictive capabilities can stay in control. And so this is how the car is able to achieve such precision control, but way beyond what the sort of typical human driving envelope is. Now, this is just one example, but to me, it's a metaphor for a larger kind of space where we can bring the technologies we have in robotics to try to help humans operate in places where it's more challenging or more difficult. For example, helping elder drivers, helping teenage drivers. And so the hope is that this might, for example, apply in a safety situation with ice, or the car suddenly slipping off a dirt road. Can an algorithm sort of turn on that effectively gives you a professional driver capability to get it back on the road? So this is still very much a research project. Any questions?
Yeah, I had a quick one. So like, how did you classify it? Just using the yaw rates of the IMU or some kind of inertial measurement?
Yeah, so there's an onboard state estimator, yeah, and so yeah, effectively in the instrumentation of the car, basically it has GPS and IMU, and that's how it does it. And
Thanks.
sure. So and in fact, one little fun thing on this project, we recently Toyota TRI had a collaboration with, in the US, we have these cars called Hot Wheels. I don't know if you have them in Australia, but they made a Hot Wheels version of our drifting car. So I've been involved with many platforms before, but never a toy car. And so we have a video online if you want to check that out. So let's see. So that was just a little prelude in terms of some of my work at TRI, which was kind of fresh in my mind. Now I want to talk a little bit about my personal journey and how it gets to like my thinking for some of our recent papers. So I did my PhD DPhil in Oxford. I worked a lot in this building. It's called the Jenkin Building. It's not as picturesque as many of the buildings in Oxford, but I have a true love for it. That's where Hugh White and the Oxford Robotics Research Group got its start. And I spent a lot of time in the basement. We had some of the earliest Sun workstations in the UK. This next to this Sun workstation is a device called a data cube that my memory serves cost about 60,000 pounds in 1987, and it could do frame grabbing and maybe some primitive edge detection at like 3 hertz. So I wanted to do vision as a PhD student, but the technology just wasn't there. And so while we had very famous vision researchers in the building, Mike Brady, Andrew Zisserman, Andrew Blake, we focused on sonar as a way to use ultrasonic ranging sensors. And this is one of the robots that I used for France. And my dream was, and obviously there are many sort of people that worked on mobile robot navigation in the early days, Hans Maravik, Rodney Brooks, Raja Shatila. And in fact, I love to give kind of historical talks, and I have to stop myself from not giving too much kind of the history side of the kind of 70s and 80s of the things that influenced my PhD thesis. But my dream was, to have a robot that could navigate by sensing the naturally occurring geometry of the world. And Hugh was a big believer in uncertain geometry. How do we have geometry and measures of uncertainty? We had this notion of using beacons, features in the environment. And so with this, we just made a simple localization system given a prior map with a common filter and some data association prediction to be able to correct the dead reckoning as shown by the triangle, and the vehicle would sort of, the dead reckoning would kind of drift off course, but by using the predictions from the map, the robot could localize itself. We also worked on how you might localize, how you might build a map given location, and tried to put them together, but we just weren't ready yet at that time. And so I'll come back to that. And so I came to MIT in 1991. In fact, I couldn't find a job in the US back then. When I finished my PhD, maybe I didn't look too hard, but I was very fortunate to get to come to MIT to work on autonomous underwater vehicles. I joined a team called the AUV lab at MIT Sea Grant, and led by Jim Bellingham, was a tremendous mentor. We built a vehicle called the Odyssey that was kind of one of several more sort of innovative vehicles at the time that tried to use as much onboard computation and sensors to sort of get rid of the tether of a remotely operated vehicle and to be truly autonomous. And so got to do a whole range of experiments, including the Arctic, the Pacific, the Mediterranean, British Columbia, and learned a lot about the ocean where things are really hard. It's really easy to lose your robot. And I got to join the faculty in '96, first in ocean engineering, and then went to, we joined mechanical, and then got the chance to join the computer science AI lab. And this is the video I showed earlier, but I live in the Stata Center, which is a sort of rather unique building. It's where my lab is. And this is the PR2, which we still have, and apparently still kind of works. Maybe one arm is broken, but we got a lot of use out of it for trying, early kind of SLAM results. My colleagues have used it for mobile manipulation and various things. And so in this kind of time frame, the Connect came on the scene and some good stereo algorithms. And I think there was a real big bump in performance in SLAM with the notion of using pose graphs and doing smoothing and mapping. I'm very indebted to Frank Dellert, who's been a wonderful collaborator and contributor to the community with GTSAM. And Michael Case was my postdoc who worked with was a student of Frank. Morris Fallon was my postdoc, who's at Oxford now. One of my earlier postdocs was Paul Newman, who's now at Oxford, just who did his PhD in Sydney. And so there are all these sort of connections in this kind of SLAM family. And despite the fact of, if I would give one complaint about Hugh, I don't know if anyone of you have ever heard him say that SLAM is solved. And so I've been fighting the SLAM is solved for 35 years. I think it's not solved, and I'll try to tell you why. And so certainly for an underwater environment, we've been involved in different kinds of experiments over the years, different ways of using SLAM, or trying to do cooperative localization, which is sort of a navigation with moving beacons with multiple vehicles. And so my research group today, so I'm very fortunate to have about 10, 11 grad students. This is a picture from about 6 months ago. Let's see, I just want to check the chat. And if you, great. And so my students are kind of a mix of folks that, a lot of mechanical engineering students that have sort of transitioned into robotics, a couple of Navy officers that really love the ocean, want to develop vehicles that can help them accomplish their tasks better, involved with the MIT Woods Hole Joint Program in ocean engineering and have wonderful collaborators at Woods Hole. Let's see, so I picked for this talk to talk about some recent papers, because in the past I think I've done a lot more on the history and not as much on the newer stuff. So some of this is a little bit hot off the press, but we've been fortunate this year that the group, it was obviously hard during COVID, but we were able to bring people back together, get on campus. And if you came to my lab, and sometimes when I give a talk in my lab, I'll actually walk around with my laptop in the lab, but I didn't try that tonight, I'm at home. But that, to be honest, I almost feel we had better demos 10 years ago than we have now, because the style of papers today tend to be more driven towards either isolating an algorithmic issue or working on, say, machine learning, applying processing data sets such as the Kitty data set or the YCB data set, and doing a lot of work of benchmark comparisons against other techniques and ablation studies and all the things that reviewers want to see in a modern paper, which obviously we need. But I do believe I was part of the group of about a dozen faculty that started the RSS conference back around 2005 with Sebastian Thrun, Nick Roy, and others. And I do believe that if we think of robotic science and systems, the systems component is really important. And so I'm trying to push my students to try to trust me that we could do a little bit more systems work, trying to put the different pieces together to truly take stock of where we are. And so, so I chose today to talk about discrete continuous smoothing and mapping, DCSAM, which is led the work of my student Kevin Doherty in collaboration with a few other students. And then this second is a work led by my student Ziqi Liu on SLAM-supported self-training for 3D object pose estimation, and then work led by my student Carol Jiahui Fu on robust change detection based on neural descriptor fields. And so I'll probably talk the most about the first two and a little bit about the last one if there's time. And then time permitting, I want to do a sort of a historical perspective and sort of future outlook. So if I had to summarize the recent research in our group, and I always imagine if Hugh was attending the talk, he'd say, John, how are you still working on your PhD thesis after all these years? It's time to give it up and move on. But I believe that there's a sort of central challenge of developing semantic representations of the environment, understanding the worlds in terms of objects, both in terms of the physics, in terms of like how different objects, knowing what is an object and what are its affordances and detecting changes, and then being able to describe the world in more human terms. In the self-driving space, we had the Velodyne laser scanner as this amazing sensor that gave us 1 million data points a second, and we could see this rich visual representation in terms of point clouds with our eyes. But it's actually challenging for a robot to make sense of that, and to the extent that the robot can make sense of it, I believe it's challenging to do things like detect changes, to understand the sort of structure of the world, and also to relate to humans. I want to describe the world in more human level terms. And so our key activities are sort of on inference and representations for, I'll steal Andy Davison's term, spatial AI. Where am I? What objects are around me? And in particular, I want to work on situations with high ambiguity. A lot of work today in robotics and SLAM with the right sensor, with the right calibration, the right sort of match of your sensor to the environment, things can work pretty well, but sometimes they fail. And some implementations have a certain fingers crossed aspect to them. And it's really like, how do we deal with ambiguities and uncertainties? And if I want to trace that back to sort of the heart of the issue, I think some of it comes from dealing with non-Gaussian uncertainties. When we have data association or loop closing situations where if we make a sort of choice that's wrong, does everything fall apart? And so last year, I won't talk about it today, but we had a paper during COVID. I had a new student work on the challenge of doing SLAM with just playing cards as landmarks, which may not seem very challenging, but the flip ambiguity, say of like a 10 of hearts or an 8 of hearts, if your representation isn't specifically tailored to deal with those kind of objects, if your robot's uncertain whether it's approaching, say, from the north or the south, and it applies with a great big pose uncertainty, and it applies the wrong update, everything will sort of fall apart. And so what we want to do is come up with a situation that can be smarter about being able to recover if it makes wrong decisions, or sort of be more tolerant of multimodal ambiguities. Let's see. So some recent papers. So I'm really, the group's been working really hard, and we had a big push for the IROS deadline with a few IROS RAL papers. And so things I won't talk about today, we're working on a technique to enable an AUV to collaborate with a human scuba diver to help the scuba diver navigate. If anyone ever uses like Strava for like running or cycling, which I use it for cycling, imagine having Strava underwater. An ability like an AUV could be a mobile positioning beacon that could circle around a diver, localize it, and then use its own precise knowledge to effectively give the diver GPS. We have another push in using, looking at non-Gaussian inference. And my student, Chad Wang, we've got a paper in RAL and just got a paper accepted for TRO related to normalizing flows for SLAM and ambiguous situations. These are still very computationally expensive, but we're doing them as sort of reference solutions to try to better understand different techniques. Let's see, Kevin has a paper on sparsification for postgraph SLAM. Let's see, but what I want to focus on is, first I'm going to talk about Kevin's paper called DCSAM that I mentioned. And this was, we were in the Robust Perception and Mapping Workshop at ICRA, and we've submitted it to RAL, and it's on archive. And so let me give a shot here. And so Kevin is the most wonderful student. I'm just, I think Shoudong mentioned earlier my students, and I feel so fortunate. I've advised or co-advised 24 PhD theses, and I've had about a dozen postdocs. And I think the collective work of some of those folks, I'm just so grateful. But Kevin certainly measures up to a lot of those, you know, the folks from the past that I wish were back now. Kevin's thesis is sort of posing the question, this motivated by underwater, can we develop systems that could have sort of a long-term learning capability that could maintaining an economical and semantic representation. I think semantic representations in terms of object can be more efficient and compact and help with vehicles that are greatly computation limited. But how do we, can we do that while achieving the sort of robustness and rigor that we'd like to have trustworthy autonomous systems? So I invite you to check out Kevin's website. He's published a lot of papers, a lot of code, and this is, and the general framework of Kevin's work is trying to do robust semantic SLAM. And in a semantic SLAM formulation, you've got your robot poses and your objects or landmarks, but you also have some discrete decision variables for the classes of objects. Like, is that object a car? Is that a truck, or a coffee mug, or a book? And obviously, there are great representational questions. How do you represent trees? How do you represent sofas and clothing? And obviously, there are a lot of tricky questions. But I also want to point out that there's some wonderful work in semantic SLAM. For example, Nikolai Atanesov, who's now at UCSD, building on work he did at UPenn. I think semantic SLAM is a really interesting problem because it brings together the continuous and discrete aspects of the SLAM problem and kind of puts them together. And obviously this is in the whole spirit of, if I've seen further, I've stood on the shoulders of giants of the great work of folks like Jose Nira and Juan Domingo Tardos on data association with joint compatibility and all the work in multiple target tracking and so forth. But in this framework, what we'd like to do, and I'm going to use a few of Kevin's slides here to try to sell this why we want semantic SLAM. And a lot of times, your mission plans rely on this sort of a more symbolic understanding of the world, knowing about objects. Clearly, things like semantic segmentation have made a big impact in the self-driving car space, but just labeling pixels is not necessarily enough. My dream is I want to actually have a robot that can build models that are sort of isomorphic to the world, that really match the world. And so so we have this kind of challenging estimation problem that involves data association, outlier rejection, and we can kind of pose everything into the context of a graphical model, say a factor graph. But they're really difficult. Unfortunately, that we need to deal with the mixture of continuous and discrete variables. For example, estimating contacts with the ground. There's some really wonderful work both at Oxford on ground-based robot SLAM and also at University of Michigan, the work of Jesse Grizzle's group. And so what we'd like to do is think about how do we represent the coupling between the discrete symbols and the continuous states in the inference problems. And so many of these problems can be posed as maximum a posteriori estimation over discrete and continuous spaces. So a lot of robot perceptions take the problem of finding the most likely continuous values for the continuous variables in discrete states conditioned on the measurements. And I think one of the tools we want to try to think about is how do we come up with a more general framework or more reusable kind of code modules or algorithms to try to work on this. I'll call out another great Australian SLAM researcher, Nico Sunderhoff, for example, really influential work and thought really deeply about outliers and achieving robustness. So Kevin's premise is that sort of really in the discipleship of Frank Dellard is we can use factor graphs as the representation. We can do discrete continuous factor graphs where we have a combination of discrete variables and continuous variables. For example, the shown here in pink and blue. And so if you, but the challenge is that many existing off-the-shelf tools don't really match to the hybrid problems. If you have more of a continuous problem or discrete problem, there's obviously lots and lots of tools. And there are existing kind of solutions, but what Kevin sort of had this insight of, can we come up with a more generic way of solving these or formulating these discrete continuous problems? And so we're living in a regime, unfortunately, due to the curse of dimensionality, where the things are intractable, and it's generally hard to come up with certainly impossible to come up with optimal solutions. But can we come up with, and as the hypotheses proliferate in the discrete space, it leads to this curse of dimensionality. But what we believe is that there can be good tools and good heuristics that can let us to attack this sort of broader class of problems with some generic tools. And so DCSAM is a library that extends GTSAM to the case of hybrid factor graphs. It uses efficient local optimization using ISAM2, and then anyone can write their own custom solvers to kind of fit in on top of this. And so, oh, sorry, and so I invite you to look at our marine robotics group, GitHub, and so we have a number of packages that are open source there, and just look at marine robotics group /DCSAM for Kevin's code. And so, and a key insight is that many of these problems can be just easily be decomposed into subproblems, so that an easier to solve discrete problem, an easier to solve continuous problem. And Kevin has a number of examples in the paper. And the key approach is to use an alternating optimization approach, alternating between argmax over discrete variables and argmax over continuous variables. And we show in the paper how this leads to a sort of monotonic improvement. Now, there's more work to be done in terms of the rate of improvement and some of the sort of broader utilization. But what we've done is we've shown how on a pretty broad class of different problems that are in this domain, that we get competitive results just with this more generic library. And so, for example, here's an example for doing some solving pose graphs and sort of comparing with, for example, G and C, which obviously is really strong approach. So the goal is to attack these sort of tightly coupled geometric and semantic perception problems. And so Kevin had earlier published a paper at ICRA 2020 on mixture models for robust semantic SLAM. And effectively, we've re-implemented that work, which was his master's thesis, with this more generic library that's also applicable to other states. So here's a video of processing one of the kitty sequences. So our paper has 3 of the kitty sequences that tend to have loops in them. And obviously, so we're using cars and trucks as semantics classes for doing a landmark-based SLAM problem with loop closing, just classifying the discrete states and the classes of the objects and the continuous states. Now, obviously, the parked cars might not necessarily be the best sort of long-term representation for mapping the world, because the parked cars are going to move to different places. But it's actually, Kitty has been a wonderful benchmark to sort of test and try different ideas. And because it's been used in so many different domains by so many other researchers, Kevin's had good luck showing the sort of how performant and in a general way that his code is with the Kitty data set, as well as many other data sets. So I invite you to look at our code for this. And so there's a couple QR codes there, but we believe the contributions in an open source code that extends GTSAM to these hybrid factor graphs, coupled with a new alternating solver that jumps between the discrete and continuous variables. And there's more work in progress on recovering uncertainty and doing incremental inference. So let's see, how am I doing on time here? 8:37. So do you want to make this kind of interactive? Like anybody want to ask any questions now, or should I press on? And thank you for all your attention.
Yeah, I think we can have any question that people want to ask now. I think one question I have is for the discrete continuous problem. We can imagine probably more local minimums exist than the traditional SLAM. So the traditional SLAM, we know that the convergence can be improved by different methodology, different tricks, and so on. So DC SLAM probably there are also some kind of tricks. And one you're talking about is alternating minimization. So this is kind of algorithm level. So my question is, do you think the number of minimum in DC SLAM is also maybe not as many as we thought?
Sure. I think that's a great question. I'm going to ask Kevin in his PhD defense or in his thesis. I think that so far we've been sort of investigating some different problem classes empirically, and we've I guess so. If I go to my former student David Rosen has actually been a great mentor and collaborator with Kevin. David is now at Northeastern, and David did the SE Sync work and thinks about sort of the certifying SLAM solutions and some of these questions, and I actually have other students in my group that are thinking about related problems in terms of for example, for range-based navigation of underwater vehicles. My student Alan Papalia, but I think what David might say, but David's very careful in how he says things and much more careful than me, that nature, maybe this is Kevin, nature is not always out to get you. So the worst case can be really, really worst case. But there seems to be something about the SLAM problem that under a lot of conditions, things kind of work out. And in fact, so David Rosen's been sort of trying to quantify how the difficulty of finding optimal solutions depends on what the noise levels are. And for sufficiently high levels of noise, things get really challenging. But for sufficiently lower levels of noise, there's the feeling that you can generally do okay. So I realize that's somewhat kind of hand wavy answer, but why don't we come back to it at the end if there's time? But basically, it's a great question, and I think the question being, are there more local minima, and how does it handle it? Okay.
So do you have time for another question? Yeah, do you have time?
Yeah, go for it, Joshua. Yeah, please.
Yeah, thanks. So I'm a student. I just had a question. I didn't understand the meaning of alternating between continuous and discrete in this kind of the factor graph construction.
Sure. So I think the idea is that if you're trying to solve, you're iterating between trying to solve for the, let me go back here. So you want to find, I'll try to use this one. So at each iteration, you're trying to find a new value of the, so one way of looking at it is with the pictures here. Think of each sort of discrete time step sort of solution as like one horizontal slice. And then you have this continuous variable sort of error surface. And so the idea of first you solve for the discrete variables conditioned on the estimate that you have now for the continuous variables. And then say to get, so you're basically going to find what DI plus 1 should be conditioned on CI. And then assuming you've assumed the value of DI plus 1 that you just got, let's find the next value for the continuous variable. So think of it as sort of jumping from one. So if you froze all the discrete variables, you'd have a well-defined continuous error surface. Let's try to solve that problem. Okay, now let's take that answer. Let's freeze all the continuous variables and solve for the discrete problem, the next iterate. And then that lets you jump to a new set of discrete variables and then freeze those. And then you get a new error surface shown here on the right, and then solve for the next value of the iteration for the continuous variable, and do that iteratively. And the paper shows a proof that this gives you a monotonic improvement
in the cost function of the field, like navigates to the minimum.
Well, okay, so this is, I think it goes back to Shoudong's question. So it's easy to show that your answer is going to improve and go towards an extremum of the function, but not necessarily the optimal one. So I think there's a larger question about where you are in the overall error surface for the global problem.
Okay, thanks, John. I think that's a
Yeah,
good answer.
great. So I'll go on and we'll come back to that if there's time at the end. It's great to give me these tough questions. Okay, and obviously all right. So how are we doing? So about 42 minutes in. Let's going to switch now. So in terms of this object-based navigation, another piece of it that I didn't mention is that we're trying to use modern machine learning tools to detect the objects. And so this is my work so what Ziqi Lu has been looking at is how can we create improved 6-degree of freedom object pose estimators that we can use to get the objects, the landmarks, that we can then put into the estimation machinery. And so this slide references a whole range of previous work that there's really been some excellent work out there, especially in the computer vision and robotics communities for detecting objects. Often they're for manipulation tasks or situations where there might be a pile of cluttered objects. And we find it surprising that not more people have looked at trying to truly use objects for SLAM. And there's a question about explicit like bounding box or geometric representations versus more implicit, either TSDF or more recently NERF-based representations. And I'll come back to that later. So, but what we want to do is we want to take my dream is to take robot captured images, use 6-degree freedom object pose estimators such as DOPE and other kind of techniques, and then feed it into optimization techniques like GTSAM, DCSAM, and produce an object level map. So imagine a robot that has a sort of a object level pose graph of the world with uncertainties. And so that's kind of our dream. And so what we found is that most most object pose estimators, they tend to be trained from data, from sort of human labeled data off the internet or different kind of sequences. When you take from the training set and you want to actually try it on your robot, it typically does pretty poorly. And so a key challenge is the domain adaptation problem, or the domain gap. If what you train your system on and what you test it on are vastly different, you're going to get poor performance. And so this is an example of a detector called DOPE that's trained on the YCB object data set coming out of from maybe 5-6 years ago. And so DOPE was published first in Coral 2018. And so like the Cheez-It box, the spam cam, you know, they're sitting around our lab. We're using the YCB objects, and manually annotating the robot captured data is tedious and limits the potential. My dream is a robot that can sort of learn about the world, maybe be bootstrapped by a prior algorithm, but then try to be better. So what we're proposing is a SLAM supported self-training. So the key thing of SLAM is getting the pose information can be a self-supervisory signal to let a robot train in the target domain to get better object pose estimation performance. And so, if we look at various kind of previous research, there's a lot of work out there in self-supervised learning and trying to address the domain adaptation problem. What our method is trying to do is we take labeled image data and pre-train a posed estimator. We can use that as a robot in the world. It can predict where the object poses should be. The robot can collect images. And what we're doing is we're building a pose graph. So we're taking, so they say to a person with a hammer, everything's a nail. My hammer is a SLAM pose graph. I think of the world in terms of pose graphs. And so we have the robot traveling through a set of poses, observing different objects. And what we're going to do is take those object position estimates. We're going to use SLAM to do robust optimization of get the object and landmark locations. But then we're going to use our predicted camera poses, object to camera poses, and optimize them to get pseudo labels. So we can take the pre-trained detector and pull out pseudo labels to use to guide self-training. And then if you think of the left half here as robust estimation to build a consistent scene representation, but then semi-supervised learning to improve the object pose estimation. So we're concurrently using these object models that we started with to navigate, but then using our navigation to improve the object pose model. So it's sort of like that, which came first, the chicken or the egg, or the self kind of bootstrapping that is sort of at the heart of the SLAM problem. But related here is how do you get the uncertainties? And so a related component of this is doing automatic covariance tuning. And so we incorporate the pose prediction covariances as variables into a joint optimization. And then we use the same trick in alternating minimization to couple the standard pose graph optimization loss, solve first, and then solve for and close from the optimal covariances, and then iterate back and forth. And so, so how does it work? Well, on the video here on the left shows the initial detector that I showed before. And once we've done the self-training, we get this, look how, so I want you to think how much stabler the lower object pose estimates are versus the top. And I have this saying sometimes I say to my computer vision colleagues, why does computer vision work, machine learning work for everyone else and not for me? As a roboticist, I want to have a robot that can just understand where objects are in the world. And the sort of state-of-the-art algorithms trained off the internet typically don't work too well with robots. So we did a series of experiments. One is using the YCP videos, which are all quite short, but just comparing the left on the right, the initial versus the pre-trained versus the self-trained. With the initial approach, we were getting about, say, a 15% outlier rate on this sequence. It drops to 2% on this sequence, or 30% on this sequence, dropped to 8% on this sequence. Now, what's happening behind the hood? We're using OrbSlam 3 to do the camera odometry. we're using DOPE, the Deep Object Pose Estimator from Tremblay et al. That's pre-trained on some synthetic data using an NVIDIA simulator. We've done some very simple robot experiments, still in the very finger crossed stage of having like circumnavigating a single object. And I just am like striving to try to plead with the students to build the sort of larger systems that I really believe we're capable of doing. But at a component level, we're pretty confident that we're able to get, say, from 87% detection to 99.8% detection to get those really stable landmarks. Okay, so check out our paper. It's coming up in Japan in IROS 23. Only Kevin from my group is going to get to go to IROS. It's a little too far, COVID, everything, but hopefully some of you will make it there. And let's see. So let me continue on. I've got about 10 minutes left. I'm just going to give you a little flavor of my student Jiahui Fu's work, Carol, she goes by. And here the work is using some ideas from neural descriptor fields. I'm sure you're aware that NERFs are taking the world of computer vision by storm, and they're quite phenomenal in what we see and what they're doing. And so I'm not doing justice to Carol's talk. I've really kind of decimated the talk for the time. But what I've kind of given as a challenge, I like to use simple objects as challenge problems, playing cards or coffee mugs or chairs, just books, simple objects. And what Carol has developed in the IROS is sort of one part of a multi-part sequence. We just submitted a paper to ICRA that if time permitting, I'll say a little bit about just to flavor the idea. But the idea is to use a neural descriptor field to describe an object, such as a coffee mug, and to be able to, what we want to do is change detection. So going way back to the early days of SLAM, a real challenge was this whole approach is based on assuming that the world doesn't change. How do we detect that change happens and update the map? And so why don't I just show a couple of her videos. So here's, she's done some tests in sim and some tests, limited tests with real data. So here are some simulated observations of coffee mugs. And what we've, she's able to build these neural descriptor field implicit representations of the mugs that can be sort of clustered and then can be used to do change detection. Here's an example with some real objects. So in our mocap room upstairs, navigating around a table with various sort of coffee mugs placed on it. And the algorithm is able to detect changes in the position. So we drive around once, change the position of a few mugs, and then be able to detect what's changed. So if let's see, if I so for change detection, Carol's able to achieve a significant jump in improvement over several kind of baselines in terms of and that's for the synthetic sequences and also for the real sequences. And so as a sort of artifact, you're also getting reconstructed, you can reconstruct the locations of objects in the world. So actually where this is kind of going, let me, actually, I think I'm going to jump a little bit out of sequence. Let me just, this is a picture from Carol's ICRA paper, which we just submitted this week. And so we call it News Neural SE3 Equivariant Embeddings for Object-Based SLAM. So what Carol's done now is taken these neural descriptor fields to capture the objects, say the coffee mugs, and coupling it with the ability to get also implicitly represent the transform from the camera pose to the object. And so what we're striving towards is to get a sort of a NERF-like representation of the world with coupled to a pose graph. So we can try to use some of the sort of benefits of the sort of the historical, what we've learned about pose graphs and SLAM and loop closing and various sorts of things, but then couple that to more of an implicit, flexible, generalizable representation for objects. So this is very much kind of work in progress, but just submitted the paper. Forgive me, I'm just going to go backwards and jump back here to where I was in that. So let's see. So time-wise, 8:54. I want to respect the time there, which must be 10:54 a.m. So I've given you this sort of little sampling of 3 of our recent papers. And to try to conclude, I want to give you sort of my gut feeling is I remain optimistic for basic university research in navigation and mapping. To me, the questions, where am I? What is where in the environment? They're timeless research questions. And they're still, they can lead us to more general kind of techniques, I believe, for critical problems in perception and in estimation. I had in my history talks, I talk about Rodney Brooks, obviously a famous Australian roboticist, probably one of the true pioneers in mobile robots, along with Hans Marvik and Raja Shatila. And Rod was from Adelaide, and he wrote a very influential paper in 1986. I've even got it in my talk. I could show you if that mobile robots sense their environment and receive error-laden read-ins. They try to move a certain distance direction and do so only approximately. It may be possible and it may be necessary to build mobile robot navigation and mapping algorithms that explicitly represent these uncertainties, but still provide robust performance. And he had a very early fingers crossed vision-based navigation approach with topological maps, but he wrote much remains to be done in 1986. And I think it's just as much true today. Many fundamental issues. And I think the question of representation, explicit versus implicit, some of the new neural based representations, what the new things coming from machine learning, like transformers and foundation models, how do we couple all that to the inference techniques that we know we need? And my dream is to enable lifelong self-learning, robots that really learn about the world, maybe through mobile manipulation, through changing and moving objects and understanding the world. And I'm a big believer in this sort of moving towards more symbolic object-based representations to help with human-robot interaction. And so let's see. And so like some of the things we're working on in progress is being able to actively look for objects and maybe do it with the lights off, maybe just almost copying some underwater kind of settings when the detectors don't work as well. How do you make systems that are robust? And I guess I'll try to conclude with this slide, but I've used this for 20 years. I think of why robot navigation and mapping is difficult. I think of these axes of representation, inference, systems, and autonomy. And so historically, we've moved from more metrical, topological representations. Dense representations came in with things like the Connect and the Velodyne, TSDFs, and we're trying to do things in terms of objects and semantic representations. And the biologists think about the difference for animals between their allocentric versus egocentric. And this is where, Mike Milford was a pioneer with RatSlam, and I collaborate with a guy named Mike Hassimo here who studies animal navigation. And there's evidence that deep in the brain, in the entorhinal cortex and in the hippocampus, that to form memories formation is coupled to these very metrical understanding of objects and places and location in the world. I feel like that's sort of necessary in robotics. And obviously we have a very challenging high dimensional state estimation problem that's mixed, continuous, discrete with data association and all sorts of other challenges. And then we need to bring in machine learning techniques and try to use learned models robustly. But I think it's not enough just to work on canned data sets. We need to couple perception to planning and control and go from demo to deployment to build systems that are sort of truly robust. And so this is the kind of landscape that I've been trying to work on, and I think there's still a lot of great work to be done. So I think I'll stop there and answer any questions.
Okay, thanks, John, for the very fantastic talk. I think from the history of SLAM and also the state of art and also autonomous driving. I think if you're happy to stay for another 10-15 minutes, I think we want to ask you more questions.
Please,
maybe
for sure, yeah.
Completely technical, but maybe also other more general questions.
Please, yeah. And if this is there, I just had a couple more pictures, but let me just show. This is from the SLAM Summer School in 2002. And if you guys recognize any familiar faces there. I don't think you were at that one, Dissa, right? You probably went to the next one.
Yeah, I don't think I was there actually. Yeah.
Eduardo was there. Eduardo was there.
Yeah.
Eduardo in the green shirt.
This is
And
the
there's
Hendrix
Sebastian
one.
Frun, Hugh Dorrant-White,
Yeah.
Mike Montemerlo is there. He's the head of localization for the Google car. There's Wolfram Burgard. And then the SLAM 2004 summer school. There's Eduardo again, and Andy Davison, Paul Newman, Brian Eustace, who I mentioned earlier, the Toyota stuff. You know, it's been like it's an incredible family. You know, the people that love SLAM. Maybe anyway. So why don't I'll stop with the memory lane stuff. Why don't I go to the pictures? You can turn your cameras on if you want, or I can go back if there are any specific questions. And any questions? Anybody in the chat? Someone said,
Yeah,
the pioneer robots.
maybe
Yeah.
maybe I can start from one. So
I should grab some
currently-
paper for your questions because you're going to give me hard questions. Yeah. Go ahead.
Yeah, I start from a general one. Currently, I think robotics PhD students has a lot of opportunity. For example, interns for like big companies like autonomous driving or something. They are looking for people like PhD students for doing interns in different companies. So, what's your view of PhD student doing interns in the?
Well, I'll be honest. It's I had a goal this summer to build an object-based SLAM system, and then 5 of my students did internships, and so I love them. But 2 went to Facebook, 2 went to Microsoft, and 1 went to a startup kind of internship. And so I feel like I wish they were in the lab in the summer, but in our summer, you know, this past few months. But I see how, especially after COVID, how valuable it was for them to be in a real company with the real colleagues. And so they came back, they're so full of life that I think it was good for them to do it. So my feeling is you should do 1 internship is probably optimal. Doing it twice is okay. More than twice is too many. So David Rosa and Julian Straub, they probably did 3. That's too many. But 1 internship, I think it's good to have that experience. Even though the lab, it's sad not to have. We were very fortunate. We had 3 ICRA submissions. You know, maybe we would have more ICRA submissions if they didn't do the Northern Hemisphere summer internship. But yeah, it's probably good for them. What do you think?
Yeah, I want to ask your opinion. Yeah, I think having some experience is good, but as you said, probably too long time staying in industry might be, it's a trade-off.
Too many.
Right?
Too much.
Yeah, Sarah, do you have some question? Or?
Oh, no, thanks, John. It's a fantastic, as usual, fantastic presentation.
Oh, my pleasure.
Yeah. My question is relating to how humans normally navigate in environment versus what the robots are doing. So it starts with kind of a point-based SLAM and now moving towards object-based SLAM. In human navigation, we don't really care about accuracy that much. So we are looking at objects, landmarks, and going towards achieving a particular task. So do you think with your old experience in SLAM, it is going towards in that direction so that it is moving from points to now objects, and now next phase might be not much of accuracy but to achieve a certain task?
Yeah, that's a great question. And I have colleagues like Leslie Kielbling have asked me for years, like, why do you care so much about accuracy? I don't, Rodney Brooks would say, I don't know where I am. But so this might be almost more controversial, and I'm not a biologist, but I feel that even though we don't think we have an accurate model of the world, I think that our innate intelligence, we actually do have, at least in a local reference frame, quite accurate understanding of where things are. And so even if we can't express it, I feel that it's really about getting, I would like to, so I think you're right, we might be able to move away from some of the point-based metrical stuff, especially with some of the sort of neural representations of objects. But I feel that accuracy matters, and it's really because we want robustness. If you show the video of the self-supervised training, like seeing the object detections that jump all over the place versus the ones that are rock solid. People will work on, say, manipulation, giving the very uncertain perception, and that's a good problem. But if you just know where the object is, pick it up. But I have trouble expressing it, but I believe we're still going to need accuracy. It's a short version.
Right. So is that, John, just one more follow-up from
Yeah,
that.
yeah, sure.
Is that because the humans have more insight and knowledge about the whole environment and aspects so that they can live with without that much of accuracy? I got your point. We need a certain accuracy. For example, if I have to go from my home to the city, I roughly know how many kilometers it is, but I don't know exactly what it is.
Yeah.
And when I go there, there are different landmarks.
Yeah.
But we are using a much more maybe cognitive analysis on that so that it can compensate for all the accuracies that we are missing.
Right. No, those are great questions. I think I view it as a kind of a scaffolding where, and Mike Milford might say the opposite, or I don't want to put words in his mouth, but looking at his older papers. But my view is from like grid cells and place cells, Mike Hasimo, and there's this evidence of this very metrical machinery deep in the brain, and then the ability to sort of have memories and objects and reason builds on top of that. And so it's almost like, like the autonomic systems, like you don't control your beating heart. I almost believe there's like an autonomic intelligence that's not consciously accessible, but it's kind of subconsciously, I am computing that maybe this is about, 7 inches. I should use metric for this audience, but like, and so, but this is one reason it's such a fascinating problem, because I think they're just these rich questions, and I don't know the answers.
Thanks, John. Jaime, you have hands up.
Yeah. Jaime?
Yeah, sorry. It's just that he was on the... Hi, John. Thanks very much for the presentation. Mine a little bit more technical. So you just touched upon this SLAM with normalizing flows, and I was just wondering whether you've chosen the normalizing flows for the distribution modeling over some of the other more generative models or VAEs because of the big. I mean, is that because you can recover the exact distribution versus the other models?
Yes, pretty much yes. And I'm happy to send me your email. I'll send you our papers and welcome any criticism.
I'll put it in the chat.
So we had a project called task-aware non-Gaussian inference, where the goal was to, with my colleague Jonathan Howe, to try to understand these situations with ambiguities, and then not just be able to represent the uncertainty, but then connect it back to the motion and the sensing to disambiguate. So to choose the actions that best reduce the multiple kind of modes. And so, but we tried the normalizing flows as a sort of more general technique to try to capture these more arbitrary distributions. And they work well for us, but still a bit slow. But let me tell you, we did something else which is way slow. Are you familiar with nested sampling, which is something my student discovered some really rich literature for, believe it or not, astronomy. So the astronomers have very challenging, limited data sets that they can't represent with Gaussians, and this nested sampling is a sampling technique that it scales. Like as you maybe can't go more than a state space size of 100, but they can really capture the distributions well. And so we're using, we coupled that using a public domain package called Dynasty Diffactographs to at least try to represent what is the reference solution for some of these problems. And and then to try for our robots to try to do more heuristic methods that are more hopeful to run in real time, and at least try to compare them against, are they getting the right answer? But the short version is that the normalized, it's pretty much exactly what you said, is we chose the normalizing flows because in theory, they can capture quite a wide variety of distributions.
I think there's a question in the chat asking the 6 degree of freedom post estimation. are you using visual data only, or you also use
Yeah,
inertial?
we're using vision only. And so inertial would definitely help. LiDAR, I've used LiDAR in the self-driving context, and I believe in LiDAR, like for improving safety, but it's not a panacea. I think, so let's see. Inertia would help if you have better odometry. There's a sort of trade-off between your sort of the proprioceptive motion and by knowing your motion more accurately, this sort of pseudo labeling process to improve your detector would work a lot better. And so and definitely the AK active perception, that's totally what we want to do. We love that. So I'm not sure I answered, but any other questions?
Yeah, I have another question related to your opinion on autonomous driving. I think you, a few years back, you said you're not expecting to see autonomous taxi in Boston in your lifetime or something like that.
Am I wrong?
Do you still think the same, or you change your mind?
I could be wrong. I mean, I think let me just mention, I'll just share my screen. I'll say a little bit about self-driving. I'm not speaking for Toyota, just my own sort of thoughts. I'm just going to actually share something from Rodney Brooks. So what's happening today in self-driving? Do you know Rodney Brooks has a, obviously, I hope you all know Rodney Brooks is a sort of famous Australian roboticist. And Rod has this blog where he makes predictions. And sorry, the font is so small to see. But Rod basically said back in May that he really feels there's like a minimal viable product of that a person with no one else in the car, that Rod can drive in a car. And so, but there's a lot of caveats to that. And so I think that there was an article that appeared recently that most people don't realize that companies like Cruise, they use a remote operator who's not like steering the car in real time, but they're sort of making sure everything's okay. And if the car gets stuck, it can sort of tell it which direction to go. And there was an article recently where Kyle Voigt was almost sort of bragging about this, saying, look, his job is to have a service for people. He doesn't care whether there's a remote human or not. And so, so I guess if it was, and even Waymo used remote operators, although it's unclear exactly what they do. But I think in terms of the taxi driver, the taxi with no driver in my lifetime, when I said that, I did not envision that teleoperators would be so much in use today. And so an interesting question is, do the teleoperators watch one car at once, or do they watch 10 cars at once? And there's this sort of scaling. My MIT, we had this thing called, actually I'm using my Work of the Future coffee mug by chance. We did a study on the effect of technology on jobs for many industries, many different situations. And as part of that, one of the chapters or one of the report is with my colleague David Mendel, who's like an underwater roboticist, as well as an aviation expert and space and history of technology. And with his student Eric, we worked on a sort of policy document for predicting the pathways. And in this one, we talked about 4 different pathways: robotaxis, trucking, public transit, and then personal assistance vehicles. And I think that I agonized over timelines and predictions, but my gut feeling is that it's going to be a very slow rollout that's going to take a long time. And one of the things that we cite in our paper, I'll send you the link if anyone's interested. There's been a person who did an economic study of robotaxis, and he basically doesn't think they're going to be economically viable. And so I think a real question is, with a remote operator that's watching the car in real time, ready to jump in if something goes wrong as best they can, does that meet the definition of autonomous? We could sort of argue over that, but there probably will be those remotely piloted robotaxis in Manhattan in probably the next 5 years, I would say. But will it be an economically viable service? Maybe we might not know the answer for another 10 or 20 years. And we'll have to see how long I live. Please God, I'm 57. So I get
the impression that everything works fine until you have the first accident. Then it just puts such a big roadblock on everything from that point onwards.
Yeah. No. Yep. So Yeah, at the pub, I could talk more. At the pub, I could talk more. Okay.
Yeah, if there's no further question, I think we will let John finish here, and it's already it's 9:15 your time, right, in the evening.
Not too bad, but I'm going to lie down. See,
Yeah, thanks, so
my
I'm gonna
American
let-
football team had a game last night. They won, so I was up late last night watching them, the Eagles. So take care. Okay.
Thanks, John.
Yeah, thank you very much.
All right, great to see you, Jessa. I'm going to visit.
And good,
Come to
good seeing
Boston.
you. Yeah, yeah. Let
Thank
us know.
you.
Let us know.
Bye. Bye.
Bye.
Okay, bye-bye.